Okay, this is almost our last section. We have one more section after this in this chapter, but this is a new section. Section 5.5, we're going to talk about some logarithms and exponentials with a base other than e. So far, we've done natural logarithms, ln, and we've done kind of the natural exponentials, e to the x. We're going to briefly talk about other bases. So what if it's a different number? So logs and exponentials with different bases. So far, we've had the base of e. For our exponentials, we've had e to the x. That is our base of e. When we have a base of a, we're talking about any number, a to the x. This could be 2 to the x, 4 to the x, 10 to the x, it could be anything. This comes from, they are connected, so our derivatives and integrals are very similar. They're just kind of a little bit different. The definition of any exponential that's not e is based on e. It's actually e to the ln of a times x. It's kind of a, ooh, you can't really read that, can you? Let's try that again. E to the ln of a times x is kind of how you get that. So that's how we're going to develop our derivatives and integrals. So we'll use the same things as e to the x. We're just going to have this ln of a piece in there as well. We also have our logarithms. That was the ln of x, which remember we wrote as really what's happening is log base e of x. We just wanted a shortcut because we're lazy. So now we're actually going to see our logarithms spelled out with a base other than e of x. This is the same thing. If you have log base a of x, it is built off of your natural logarithm. It actually uses something called a change of base formula, which is something that you've seen before, but you may not remember. But it involves ln of x over ln of a. So we're going to have the same thing. We're going to have this idea. We're going to use ln of x, but it's just going to be divided by ln of a whenever we're using logarithms of any other base. So a couple things that you really need to remember. You need to remember that all of our exponent rules from 5.4. So we're going to be using those. So you need to remember all of that. The other thing that we need to remember is the properties of our inverse log and exponential. So we did talk about this at the beginning of the last section, that our logarithms and exponentials are opposites of each other. So even when we have different bases, that idea still applies. So what I mean by that is if we have the logarithm base a of a to the x, that log base a of a kind of just, we can go through the more technical things, but basically just cancel out. As long as the base and what you're plugging in match, then it's just x. And that also works for exponentials. As long as a and the base of the logarithm that's in the exponent match, then they basically just cancel and it's x. If you need more of an explanation, if you need more of a mathematical explanation, I can give that to you. It's kind of long and intense, which is why I don't specifically go over it, but they just basically cancel is the best way to just kind of sum that up for you guys. We also need to be able to solve, are they here? Yes, okay. We need to be able to solve these problems. So here's an example of a problem that's 3 to the x equals 1 over 81. We need to be able to solve this. So there are a couple different ways you can solve this. The best way to solve this is actually going back to ln because we have that button on our calculator. So what we can do is we can take the ln of both sides. And over here, we can use our logarithm rule and move the x in front. So we have the ln of 3 equals the ln of 1 over 81. And then we would just, to get x alone, divide both sides by the ln of 3. So x is just the ln of 1 over 81 over the ln of 3. Now, if you put that in your calculator, it actually divides out really nicely, and you get x equals -4, which is very nice. We expect some kind of crazy decimal from that, but we don't get it. We also need to be able to solve logarithms of other bases. So in this case, we kind of use that this is a log base 2. So we use the idea that if we change this into an exponential with a base of 2, that's going to cancel it out. So if we put this in the exponent of 2, that means we have to put the other side in the exponent of 2. So here, log base 2 and 2 cancel, and we just have x. Here we have 2 to the 4th. Yep. And then we have x equals 16. Okay. The other thing that you could do here, if you didn't think about that, you could do your log rule. If you had log base 2 of x equals 4. Our log rule is this base to this number is equal to this. So 2 to the 4th is equal to x. 2 to the 4th is not. Oh, it is 16. It is. 2 times 2 is 4 times 2 is 8 times 2 is 16. I'm right. I'm not crazy. 16 equals x. Either way of those solving would be fine. You just need to be comfortable with at least one of those. If you have more questions, let me know. So that's kind of our prerequisites on 5.5. What we need to talk about now is our actual calculus that involves these. So this is a printout of our derivatives of bases other than e. So you can go ahead and attach these. So if we have a to the x, what's going to happen, just like the derivative of e to the x is e to the x, the derivative of a to the x involves a to the x. It just has an extra ln of a, just like our definition has an extra ln of a from e to the x. That's where that comes from. So we just have to multiply by the ln of a. Now, if our exponent is like x squared plus 1, then we do the same thing. We write what we see, multiply by the ln of a, and then we just multiply by the derivative of the exponent. So whatever's up there, we take the derivative and put that on the end. Generally, you just leave these in one big long line and walk away. When it's a logarithm, instead of multiplying, just like our definition, this is multiplied, the ln of a is going to be divided. So when we take our derivative, it's going to be divided as well. So for ln, our derivative is 1 over x. So a logarithm, it's going to be 1 over x. We're just going to have an ln of a in the bottom with the x. Okay. I know these look like a lot, but the more that you use them, just like everything else, you'll become more familiar with them. It'll be easy to remember. Mostly these are multiple choice, so it's really just recognition. You can do this. So you have log base a of anything else. What if it was log base a of x squared plus 2 again? You would need to be able to take the derivative of that. So you still have ln of a in the bottom with what you see, u. But then when you do that, you just need to multiply on the end by the derivative of u. You can also put that on top, which is what we usually do. Remember, the derivative of ln of u was u prime over u. Well, here's our u prime over u. We're just multiplying by an ln of a in the bottom because we divide with logarithms. As far as integrals go, you only need to integrate a to the x. You're not going to have to integrate logarithms of any base. The only thing you need to integrate are exponentials of another base. And it's just the opposite of dividing a to the x, a to the x. Just instead of multiplying by 1 over a, you divide by 1 over ln of a. And then don't forget your plus c. Since you're dividing by ln of a, you can also write that as a to the x over ln of a. Either one of these is fine, but they mean the same thing. It doesn't matter. Okay. So let's just look at a few examples involving these. And that's actually it for this section. So the next day you're in class, we will be working on our last section of this chapter. So Let's find the derivative of these next couple. So we have y equals 2 to the x. There is one note that I want to add to that, just like we did the other one. So just pause, don't write that. Pause, 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 pause. I want you to make a note. Kind of helps you understand what's going on up here. When we take the derivative of e to the x, if we followed this same rule for a derivative of a to the x, then it would be the ln of that number, a to the x. Well, this case, it just happens to be e. So this would be the ln of that number, e, times e to the x. Well, ln of e is 1 times e to the x, which is just e to the x. This is really, like, you use this rule, you just didn't even know it. The derivative of e to the x is e to the x, because all this middle stuff happens. You just don't have to know that middle stuff happens. We can just put that it's e to the x. Okay, I hope that helps you understand what's going on a little bit better. So when we do this problem, now my examples are all messed up. Gosh, Miss Robinson, you're a mess. Okay, let's find the derivative of y equals 2 to the x. Well, when we look at this chart, we have an exponential ln of a times a to the x. So we have, when we take y prime, the ln, what number is there? 2 times 2 to the x. Be careful to use parentheses, and that's it. That's all you do. That's all you do for this. Be careful to use parentheses around these because you don't want this 2 to the x to accidentally end up inside the ln. If you're ever nervous about that, you can write the 2 to the x first because then it's really clear that it's not inside that ln with that other 2. And then, so let's look at one where our exponent is not just x. If we have, yeah, trig, freak out, whatever. Y equals 2 to the 3x. Well, let's look at this. We're doing the same thing that we just did with the previous problem. We just need to make sure and multiply by the derivative of our exponent. So when we have this, when we find y prime, we'll have the ln of the number base of 2 times 2 to the 3x times, if I look at my exponent, the derivative of just my exponent is 3. Maybe the best way to write this is 3 ln of 2 times 2 to the 3x. That would be acceptable. Just make sure that you're not like combining things when they shouldn't be combined. But that's really it. Let's look at another derivative problem. If we have the log base 10 of cosine of x. So same rules apply, but now we're working with our logarithm. So when we look at our logarithm, and this is going to be something where it's not just x in there. We're going to be using the second rule. So it's the ln of a on the bottom times what we see. So we have the ln of this number times whatever is here. And then we multiply its derivative. So let's see. We have 1 over, we do y prime, the ln of this number times whatever is here. So this is times cosine of x. Then we need to, once we do these two, we'll multiply by the derivative of cosine of x. The derivative of cosine of x is negative sine of x. So this is times negative sine of x. So you can stop here, or there is a little bit to simplify. So we do have sine, this is over 1, and we do have sine divided by cosine. Sine divided by cosine is tangent. So since there's a negative, it's negative tangent of x over the ln of 10. Would be our simplified answer, and that's most likely what you would see. Now, one more log problem. And remember those properties. They don't go away just because we have different bases. So this looks crazy, but remember, let's rewrite this first before we take our derivative. So when we rewrite this, we have log base 3 of x plus, this is a 1/2 exponent, so we can move that to the front when we make it a logarithm. It's plus because these two are times, log base 3 of x minus 1 divided by 3, so this is minus log base 3 of 3. Now, we take our derivative. So this is y, not y prime. Okay, so be careful there. Now we can take our derivative, and we just do one at a time. Log base 3 of x. Well, log base 3, we're working here. 1 over ln of 3 times x is what we get. 1 over ln of 3 times x. And then we have plus 1/2 times, we'll have 1 over, again, the ln of 3 times x minus 1 times the derivative of x minus 1 is just 1, so we don't even really have to write it, minus the derivative of log base 3 of 3. This is all numbers. This is a number. Notice how there's no variables? The derivative of a number is 0. Doesn't matter what format that number comes in. Log base 3 of 3 is a number. Derivative of any number is 0. No variable. Really the only thing we're going to do to combine these, we could do 1 over x ln of 3 plus 1 over 2 ln of 3 times x minus 1. Don't add these together. It's really like there aren't super many of these questions, and they're not going to ask you to do a ton of crazy things. You already have to kind of remember a formula for this one, so they're not going to ask you to do anything nuts. So you would just stop there. Now, there are a couple things to keep in mind. We have some other rules. Just not really rules. This is more of things to remember than anything new. What is the derivative of e to the e? Well, it's a number. E is a number, e is a number. E to the e is a number. The derivative is 0. So be careful, even though these are letters, they're not variables. They are letters standing for numbers. So the same thing, that's the same exact thing, oops, for 2 to the 2. 2 to the 2, that's a number. Derivative of a number, 0. Okay. What about e to the x? E to the x, the derivative is e to the x. Don't forget that one. That should be the easiest derivative you ever take. Now x cubed, so we're combining rules. This is our regular power rule. So the derivative of x cubed is just 3x squared. And then our last derivative, be careful here and think about this for a second. X to the e. X to the e is the power rule. Bring the e down. X, subtract 1 from the exponent, e minus 1. It looks ugly, but that's exactly what we did here. Bring the 3 down, x to the 3 minus 1. We could just actually do 3 minus 1, which is how we got 3x squared. Okay. Then I know this video is getting long, but there's like a minute left. The integrals are so easy because there's also only one formula. So there's only one thing that you need to be able to integrate. The integral of 2 to the x dx. Well, when we integrate an exponential, it's just going to be 1 over ln of that number and then multiply by whatever that is. So there's nothing tricky going on. This exponent is nothing crazy. So it's 1 over the ln of 2 times 2 to the x plus c, because it's indefinite. Now we can write the 2 to the x on the top if you like, ln of 2 plus c, but both of these are fine, either way. Now, do be careful. Let's look at this last example. The integral of 2 to the negative x. Now, this is not just an x exponent. So this is an integral, so it does require u substitution. So u is negative x, which means du is negative dx. So you need a negative in there. You need to multiply a negative, which means you need a negative on the outside. So this is really the integral of 2u du. But then we're using the same rule. So 1 over our ln of the number times the function. This is just negative. So 1 over ln of the number, which is 2 in this case, times the function plus c. And then for our final answer, we just put our x back in. And we can write that up top. We could say negative 2 to the negative x over the ln of 2 plus c. Okay. So that's it. That's actually the end of this section. So that's all we need to know for derivatives of other bases. We'll do our last section at the end of this week, and then we'll start reviewing for the test. So if you have any questions, please come in and ask. But that is actually all of section 5.5. You now have an assignment in Canvas.